Hello and welcome back in our class of Foundation Engineering. So this is the second video of this program, and we are still on the chapter number 1, which is about the review of soil mechanics used in Foundation Engineering. Okay, so we'll try to continue with the same chapter today. Today we will focus on this part, section 3 of this chapter 1, which is water in soil. As you know, water is very important to consider when you are doing a foundation, when you design foundation, and actually not only foundation, any geotechnical structure, any geotechnical work you are doing, consideration of water is very important. So this is what we are talking about today. Since it is review, once again, I think you will have more detail in soil mechanics class. Okay, but this is just review. So let's go. Some people maybe think that when it comes to clay, we don't need to consider water that much. But actually, clay mineral, water with clay mineral, sometimes may have some reaction, like chemical reactions. We need to understand, okay? Yeah. So when you see for coarse-grained soil, like cobble, boulders, gravel, and sand, this kind of soil are generated by mechanical weathering. But if you take clay mineral are generated by chemical weathering. That's the difference. Okay. So if you take, for the case of coarse-grained soil, the behavior hinges on grain size distribution and the packing. But if you take the case of clay mineral, these clay mineral have like electrochemical activity. Water content significantly impact the behavior of this clay mineral. So you should be careful about that. Once you have clay in your foundation, maybe you have to be very careful about water. You need to find out what type of clay is it, and then try to see the influence of water on this clay, because it's very important. Okay, so clay mineral consists of hydrous aluminum silicate with metallic ions, like these ions. And when we do X-ray diffraction, we can see that the crystal structure with repetitive sheets. Okay, the sheets of tetrahedral silica and octahedral aluminum, something like this. This is, for example, clay A, kaolinite. Okay, B is illite. So if we take this case, for example, X-ray study, diffraction study, show that there are just repeating like this sheets, like silica sheets, gypsite sheets, and again repeating silica sheets, gypsite sheets. This is for kaolinite. Okay, I will keep this figure here. The most important part is what is coming now, because if you take the case of kaolinite, you can see that it's one by one, the sheet, one sheet by one sheet, one silica sheet, gypsite sheet. Okay, then it repeat again, silica sheet, gypsite sheet. However, if you take this one, for example, It is not same. You have silica, gypside seed, and silica before it repeat. And between them, we have potassium inside silica, gypside, and silica. Here it's different. It look like this one, but the difference is here. Instead of potassium, we have here like water, NH2O. Anyway, for this one, kaolinite, this the structure or like microscopic view or study of this is not really what is important here. What is important here is how these clays behave when you add water in them. This one, kaolinite, okay, the layer bond through hydrogen and water has minimal effect. So means if you are doing foundation and you have this type of clay, maybe you don't have to worry about too much about water, okay? That is the meaning. However, if we take, this is like just photo from Wikipedia of kaolinite. If we take this one and this one, Montmorillon, how to read this? Montmorillonite. The name is quite long. And this one, elite. Anyway, both are here. Just photo. These two have various bounding, means more complex. For example, if we take this one, Montmorillonite, that one is losing the silica acid. You see the silica acid here. It's losing the silica acid bond, and that loss will allow water and ion between layers, causing swelling. So if you add water, the clay will swell. That may be like heaving and lift your foundation. Sometimes when you have this kind of clay in your working construction site, foundation, people use lamps stabilization to reduce the Ca2 plus addition. By additioning the lamp, we are adding the Ca2 plus, and this addition will reduce the effect of water on this clay. Okay, I show you, for example, this photo is showing lamp soil stabilization method. So the white thing you are seeing is like limestone. Okay, mixing this is clay. So by doing this, it will help to minimize the effect of water on this clay. And this one, the elite layer bond with potassium and a potassium ion inhibiting water intrusion. So those avoiding soiling. This is when you have elite. So it means that if you have clay on your construction site, you better know what type of clay is it before you continue before you construct on it. Okay, anyway, let's move to next part, which is effective stress concept. I think everyone knows about effective stress. So void or pore within soil skeleton contain fluid such as air, water, or other contaminant. Hence, any load applied on the soil is partially carried by such pore fluid, in addition to being borne by soil grain. The soil grain will carry one part, and the fluid in the soil also will carry another part of load. So the load is like kind of divided. Okay. So in that case, the total stress at any given location within the soil mass induced by load can be expressed as summation of the stress contribution from the soil skeleton and the pore fluid. We can write the formula like this. This is the total stress, the effective stress, and the part that the fluid are taking. Total stress above atmospheric pressure, effective stress in the soil skeleton. So this is the part that the soil skeleton will take. And the pore fluid pressure, this one, UP. We'll keep it just here because we'll use it again. So the stress in the soil skeleton or intergranular stress is also known as effective stress. This one, the stress in the skeleton. Okay, effective stress, because it indicates that a portion of the total stress is carried by grain to grain contact, the contact between the soil grain. In the case of dry soil, for example, means there is no water, okay? The pore fluid is primarily air. And in that case, the effective stress will be the same as total stress. So it means we will not have this because the soil is dry. Total stress will be equal to effective stress. Okay. On the other hand, if we have now saturated soil, in that case, effective stress at a given location is completely dependent on the pore water pressure. If you are in a static condition, then it is easy. But in any way, if the soil is saturated, then the pore water pressure will influence everything. So in that case, if we do effective stress, sigma prime, now you know this is effective stress. For example, here, the same formula as here. Total stress minus this UW means this one is total stress, this is effective stress, and this one is the pore water pressure. So using the unit weight of soil, this is gamma, and unit weight of water, gamma W, this equation, we can write it, modify it in very useful form. We can do it like this. So unit weight of soil, gamma Z, and this is pore water pressure, unit weight of water multiplied by dW. Z here, I will explain what is dW. Z is the depth of the location from the ground surface, because we have gamma Z here, okay? And dW is the depth of the location from the groundwater table. That is the meaning. This figure can explain a little bit. So we have the water here, the level of water here, and this is your dW. This is the ground surface. From the ground surface until to the point where you want to calculate, to estimate effective stress, vertical effective stress. It's better to be precise, vertical. Then this is Z, okay? Again, this is meaning that your soil is uniform. And once again, this is, if you need more detail about this, please go to soil mechanics class. You will get more detail. This is just a review before we start the most interesting part of this program. Okay. So now, when we have a partially saturated soil, that means the soil is not dry and it's not fully saturated. There is water, but it is not fully saturated. In that case, the effective stress is governed by both pore water pressure and air pressure. Okay, this is kind of soil mechanics 2 or unsaturated soil mechanics. So for unsaturated soil containing both air and water, like in this case, with high degree of saturation, for example, if we take 85% or above, we have this formula, Bishop and Blight, I think, giving the relationship between the total stress, effective stress, air water pressure, pore water pressure, and this coefficient. So UA minus UW, this is the air pressure. We stated it here already. This one is water pressure. So this term minus this term is what we are calling in unsaturated soil mechanics matrix suction, which is very, very important in unsaturated soil mechanics. Okay. It will depend on the surface tension of water. And if you take this coefficient, I think the name is key, but I'm not sure. This parameter is parameter that ranges from 0 to 1. And it depends on the degree of saturation. Okay. So if you take in the case of the soil is saturated, okay, in that case, this key is equal to 1. So completely saturated soil. And in that case, it means that there is no air in the soil. If there is no air in the soil, means this one is 1. Once, if you have this one is 1, then we can see that we can get this formula easily. The previous formula we showed before. Okay. Try to replace this by 1. You will see that this one will go. The air water pressure will go. Then we have total stress will be equal to effective stress minus, actually plus, because there is another minus here, plus water pressure. Okay, then the effective stress will be total stress minus water pressure. Okay, I think that is all for this part. I try to make really short videos so that you can fully understand and it will help you maybe to follow. Okay, so step by step. Sorry, this first chapter is just review. After this chapter, I think we will start very interesting things. Thank you very much for your time.